Greetings, I am Zhizhong Li from UIUC, and this is a collaboration with my advisor, Derek Hoiem. In research, train and test sets are usually drawn from the same pool of data, but in practice, different pools of data apply in development and deployment. A face attribute classifier that is trained on images from a developer's employees may be applied to faces from a wider demographic of Internet users. On unfamiliar data, overconfident errors appear disproportionately often. With our baseline gender recognition model, the error rate among 99% confident predictions increases to 12 times when the input is from an unseen age range. Overconfidence can cause real-world problems, such as when an automated vehicle confidently mistook a tractor-trailer for the sky. In this study, we investigate how well deep classifiers behave when faced with unfamiliar samples that are applicable but different in a structured way from those seen in training. We propose to split familiar and unfamiliar data by subcategories. For example, when classifying gender, faces outside the training age range are unfamiliar. When classifying dog versus cat, new breeds are unfamiliar, and so on. The unfamiliar samples are unknown by definition during training and validation. Therefore, approaches such as domain adaptation cannot be applied. Other works have investigated deep neural networks' erratic behavior on irrelevant data, such as on pizza images for dog versus cat classification. Our focus is confident errors of relevant images. We explore several approaches to improve the confidence estimates. We talk about ensembles and calibration in detail. Ensembles were shown to increase robustness. One member can be confidently wrong, but different members can be confidently wrong in different feature space regions. Therefore, the average predictions are better behaved. Calibration tunes the confidence to be close to the probability of error. We use temperature scaling, which was found effective for deep networks. Class scores are divided by a constant temperature T before going through the softmax layer, making the prediction more uniform and less confident for all samples. Temperature T is calibrated using a validation split. Although it has no knowledge of what is unfamiliar, we still observe its effectiveness on unfamiliar data. Distillation compacts an ensemble into a single network for efficiency. Novelty detection detects outliers and reduces their confidence. Approximate Bayesian methods aggregate different models' outputs over a distribution. For our results, we highlight two criteria. First is cross-entropy, which signifies error. Second is overconfidence, which we use cross-entropy minus entropy. When this term is positive, it means that the classifier's confidence exceeds what it should be according to the ground truth. Please see our paper for other criteria. We show that cross-entropy rises sharply with unfamiliar data. A large part of this comes from the rise in overconfidence. Different methods are able to reduce both error and overconfidence. But most importantly, we find that calibration can improve all methods for most criteria, and even the baseline model with calibration can outperform most other methods without it. Across all datasets, we find that calibrated ensembles consistently perform the best. To sum up, we highlight the issue that classifiers are often confidently wrong, especially with data underrepresented in training. We propose an experimental method to study the problem with familiar and unfamiliar data splits and several useful metrics. Among several potential solutions, temperature scaling calibration is the most effective at reducing overconfidence for a single model, while ensembles further improve accuracy and reduce overconfidence. Please download our paper for more details. Thank you for your attention.